Dear students, after studying this module, you shall be able to know about the importance of unsaturated heterocyclic compounds, design the synthesis of 5-membered unsaturated heterocyclic compounds, and understand the retroanalysis and synthesis of 6-membered unsaturated heterocyclic compounds. Do the retroanalysis and synthesis of unsaturated heterocyclic compounds containing 2 heteroatoms. Heterocyclic compounds are cyclic compounds containing heteroatoms like nitrogen, oxygen and sulfur. Heterocyclic compounds can be saturated as well as unsaturated. Unsaturated heterocyclic compounds contain double bonds and are generally aromatic in nature. Unsaturated heterocycles generally involves unstrained 5 and 6-membered rings which include pyrrole, furan, thiophene, pyridine, etc. Another large class of unsaturated heterocycles are fused to benzene rings which for pyridine, thiophene, pyrrole and furan are quinoline, benzothiophene, indole and benzofuran respectively. Unsaturated heterocycles have many applications. For example, pyridine is used as a solvent, a waterproofing agent, a rubber additive, an alcohol denaturant, furan as commercial applications as precursor in synthesis of tetrahydrofuran which is a useful solvent. Unsaturated heterocycles occur in many natural compounds and show pharmaceutical applications. For example, cladribine and pentostatin are drugs used to treat hairy cells leukemia and multiple sclerosis. Synthesis of 5-membered unsaturated heterocyclic rings. Synthesis of 2,5-dimethylfuran. The synthesis of furan can be carried out by cyclization of 1,4-diketones in the presence of an acid. Retrosynthetic analysis of 2,5-dimethylfuran as represented by the structure 1 is given in figure. The disconnection approach shows that the compound 1 can be synthesized by hexane 2,5-dione. Further, the disconnection of the compound 2 shows that 1-chloropropane 2-one and ethyl 3-oxobutanoate are the starting reagents which are shown by the structure 3 and 4 in the given figure. Let us look into the synthesis. The synthesis of 2,5-dimethylfuran 1, the target molecule is synthesized from simple and easily available starting material 1-chloropropane 2-one and explained in 3 steps. The reaction takes place in the presence of a base 1-chloropropane 2-one and ethyl 3-oxobutanoate react to give ethyl 2-acetyl 4-oxopentanoate represented by the structure 5. Next step involves the decarboxylation on heating the compound number 5 in the presence of an acid to give compound number 6. Addition of enol oxygen to the carbonyl group leads to the cyclization of 6 to give compound 7 in the step 3. This is followed by the elimination of water to give 2,5-dimethylfuran number 1 which is the required compound to be prepared. Synthesis of ethyl 2,5-dimethyl 1H pyrrole 3-carboxylate. Pyrroles can be synthesized by Pal-Knorr synthesis in which ammonia or a primary amine reacts with the 1,4-dicarbonyl compound. Here, ammonia or a primary amine is the source of nitrogen and 1,4-dicarbonyl compound provides the required number of carbons in the ring structure. Retrosynthetic analysis. Disconnecting both carbon and nitrogen bonds of a pyrrole system present in the compound ethyl 2,5-dimethyl 1H pyrrole 3 carboxylate represented by the structure 8 and 1,4-dicarbonyl compound 9 and ammonia 10. The disconnection approach for 1,4-dicarbonyl compound gives ethyl 3-oxobutanoate number 11 and 1-chloropropane-2-one represented by the structure 12 as the possible starting material. As can be seen how in the figure the cleavage of the bond takes place to give the synthons 11 and 12. Synthetic approach. The synthesis of ethyl 2,5-dimethyl 1H pyrrole 3 carboxylate represented by the structure 8 is given in figure. The target molecule is synthesized from the simple and easily available starting materials ethyl 3-oxobutanoate 11 and ammonia 10 and explained in simple steps. In the step 1, the reaction between ethyl 3-oxobutanoate given by the structure 11 and ammonia gives the corresponding amine represented by the structure 14. The compound 14 displaces the halide of 1-chloropropane-2-one structure 12 to give the new compound 15. In the step 3, the lone pair of amine in the compound 15 then attacks the carbonyl group to give the cyclized compound 16 leading to the cyclization and finally the required compound. The compound 16 loses a proton to give the double bond and shifting of the electrons neutralize the positive charge on nitrogen to give the compound 17. The compound 17 eliminates water to give ethyl 2,5-dimethyl 1H pyrrole 3 carboxylate as represented by the structure 8. The complete scheme is shown here in the figure and well evidently we are able to prepare the given organic compound following the same retrosynthetic analysis approach. Synthesis of 2-methyl-5-phenyl-thiophene. Thiophene systems can be synthesized again by Pal-Nord synthesis by reacting 1,4-dicarbonyl compounds with a source of sulfur. The retrosynthetic analysis of 2-methyl-5-phenylthiophene is given in the figure. Disconnecting both carbon and sulfur bonds give 19, which is synthesized by a reaction of 1,4-dicarbonyl compound with source of sulfur. The synthesis of 2-methyl-5-phenylthiophene is given in the figures. The target molecule is synthesized from 1,4-diketo compound and phosphorus pentoxide. As can be seen in the step 1, phosphorus pentasulfide given by the structure 21 reacts with 1-phenylpentane 1,4-dione structure 20 to give the compound number 19. The compound 19 then cyclizes to give the intermediate 23, which eliminates hydrogen sulfide to give 2-methyl-5-phenylthiophene represented by the structure 18. Synthesis of 6-membered unsaturated heterocyclic rings. The 6-membered unsaturated heterocyclic compounds include pyridine, quinoline, isoquinoline, etc. The synthesis and retrosynthesis are discussed. Synthesis of 2,6-dimethylpyridine. The general disconnections reveal that the pyridine can be synthesized by the reaction of 1,5-dicarbonyl compound with hydroxylamine. The retrosynthetic pathway of 2,6-dimethylpyridine represented by the structure 24 is explained in the figure. As it can be seen, the cleavage of the carbon nitrogen bond takes place at the two positions, leading to the formation of the double bond O compounds and the loss of the hydroxylamine. The functional group interconversion then leads to the cleavage of the carbon-carbon bond, loss of one dicarbonyl compound and leading to the synthons and the starting reagents, which in turn can then be recombined back to form the required given compound. The synthetic approach shows that 2,6-dimethylpyridine 24 is shown by the figure, wherein in the step 1 heptane 2,6-dione structure 30 reacts with hydroxylamine to give 31. The lone pairs on nitrogen in the compound 31 attacks carbonyl group to form the cyclic compound 32. In the step 3, elimination of 3 molecules of water gives 2,6-dimethylpyridine represented by the structure 24. Synthesis of quinoline. Quinolines can also be considered as benzo-fused alpha-beta unsaturated imine. Retrosynthetic analysis. The retrosynthetic analysis of quinoline represented by the structure 33 is given in figure 9. The disconnection approach suggests that the imine nucleus may be obtained from corresponding amine and alpha-beta unsaturated carbonyl compound. In the given synthesis, the substituted quinoline can be synthesized by SCOP synthesis by heating the substituted aniline and glycerol in the presence of an acid and an oxidizing agent. The synthetic pathway of quinoline structure 33 is given in figure. Here in the step 1, the glycerol on dehydration gives acrolein, to which the aniline adds in the conjugate fashion to give the N-substituted compound. This N-substituted compound represented by the structure 36 undergoes the acid catalyzed cyclization to give 1,2-dihydroquinoline 37. In the step 3, 1,2-dihydroquinoline is dehydrogenated by an oxidizing agent to give substituted quinoline. The synthesis of unsaturated heterocyclic rings with 2 heteroatoms. The unsaturated heterocyclic compounds possessing 2 heteroatoms are biologically active, synthetically useful and important heterocycles having a wide role in the medicinal chemistry. Synthesis of 3,4-dimethyl 4H isoxazole 5-one represented by the structure 38. Retrosynthetic analysis. The retrosynthetic steps for 3,4-dimethyl 4H isoxazole 5-one 38 is given in figure 11. The disconnection of isoxazoline 38 at the heteroatoms give well-known fragments beta ketoester, 2-methyl-3-oxobutyric acid, ethyl ester 39 and hydroxylamine 40. Synthesis of 3,4-dimethyl 4H isoxazole 5-one is given. This is a one-step reaction and ethyl 2-methyl-3-oxobutanoate reacts with hydroxylamine to give 3,4-dimethyl isoxazole 5,4H-one 38 represented by the structure 38 and shown in the figure. Retrosynthetic analysis. The retro scheme in figure 13 shows that the pyrazolone 5-methyl 2,4-dihydropyrazole 3-one represented by the structure 41 can be obtained from a beta keto ester 42 and hydrazine. If you look into the synthesis of 5-methyl 2,4-dihydropyrazole 3-one 41 is given in figure and explained in 2 steps. Ethyl 3-oxobutanoate reacts with the hydrazine 43 to give 44 eliminating water molecule. In the step 2, the compound 44 then cyclizes to give 5-methyl 2,4-dihydro 3H pyrazole 3-one represented by the structure 41. To summarize, the unsaturated heterocyclic compounds contain double bonds and are generally aromatic in nature. For example, pyrrole, furan, thiophene, pyridine, etc. The synthesis of furan can be carried out by the acidic cyclization of 1,4-diketone. Pyrroles can be synthesized by Pal-Nord synthesis, in which ammonia or primary amine reacts with the 1,4-dicarbonyl compound. Thiophene systems can be synthesized by Pal-Nord synthesis by reacting 1,4-dicarbonyl compounds with a source of sulfur. The disconnection approach reveals that the pyridine can be synthesized by the reaction of 1,5-dicarbonyl compound with hydroxylamine. The substituted quinoline can be synthesized by Scop synthesis by heating substituted amine, aniline and glycerol in the presence of acid and an oxidizing agent. The synthesis of 3,4-dimethyl 4H oxazole 5-one can be achieved from beta keto ester, 2-methyl 3-oxobutyric acid and ethyl ester and hydroxylamine.